Mathematics, Analysis and Approaches, Paper 1, Timezone 1, HL, November 2025, Question 11. He talks about a complex number. This is a 22-mark question, Question 11. He talks about a complex number. He wants us to show that W, which is a complex number, is in this format. And then he wants us to find the modulus and the argument of the complex number. He is also asking us to find out the roots of a complex number, W. We're going to use De Morgan's law for doing that. And the complex number can also be expressed in a+ib format. And let's see what we can do with this one. Find out a square and b square. And using that, we can find out what is tan of pi by 12 in the form of p plus q root 3. That's the complex number. Now we're going to be multiplying the numerator and the denominator by the conjugate of the denominator. So the conjugate of the denominator is simply going to be 1 minus I root 3 divided by 1 minus I root 3. I'm going to quickly multiply this. So this is going to be 4i minus 4 root 3, and then I'll have I into I, which is a minus 1, and in the denominator I'll have a plus b into a minus b, which is a square minus b square. So the numerator would simply have 4 plus 4 root 3 divided by 1 minus of minus 3. Again, I square is going to be a minus 1, and then root 3 square is going to be simply a 3. So I can take a 4 common out from the numerator. I'll have I plus root 3 divided by 1 plus 3, and that is going to get cancelled. That's simply going to be 4 times of root 3 plus I divided by 4, and hence I can go ahead and say the W is root 3 plus I. Great. Let's look at the next part of the question. The modulus of W is nothing but root of root 3 the whole square plus 1 square. If I have the complex number, let's say Z as equal to a plus ib, then the modulus of that is simply root of a square plus b square. Now this is equal to root of 3 plus 1, which is root 4, and that's simply a 2. That's your mod. What's the argument? The argument of W is simply equal to tan inverse of 1 by root 3. You can either write a pi by 6, or you can also say 30 degrees. That should be good enough. Again, the reason why it is tan inverse of y by x is because both are positive and they will fall in the first quadrant. Depending on the quadrant it lies in, the value of it will change. Now, this is one way of finding the argument. What I generally do is to write this as W is equal to, I multiply the argument and divide it by the argument, and I compare it with the polar form, which is R cos theta plus I sin theta. And then from here I say, okay, cos theta is going to be root 3 by 2, and sin theta is going to be 1 over 2. Then I explore, okay, what is that one particular value of theta which is satisfying both of it, and this is going to be a pi by 6. Great. Let's look at the next part. Alright, so a complex number Z can be written as R cos theta plus I sin theta. Now this is going to be the polar form. This is the exponential form where R is equal to e to the power of I theta, and this is basically Cartesian form. And Z is equal to R cos theta plus I sin theta can also be written as R cis theta. So let's consider this complex number Z root 3 plus I. I know that the modulus of that is the 2, and then the argument of Z is pi by 6. So W can be written as 2 e to the power of I pi by 6. What does De Morgan's law here state? Cos theta plus I sin theta whole to the power of n is simply equal to cos n theta plus I sin n theta. This is what it states. we're not going to be using this to find the roots of the complex number. In a way, we're using it, but then we're going to make a small change. When we are finding the root of a complex number, let's say z to the power 1 over n, we're going to write this as r to the power 1 over n into e to the power of I 2k pi plus theta, and this is divided by n. Now this is going to be the formula that we're going to be using, and the value for k is going to start from a 0 and it's going to go till n minus 1. It's not going to be equal to n or above it. Keep that in mind, please. W to the power 1 over 2 is going to be equal to 2 to the power 1 over 2 into e to the power of I 2k pi plus pi by 6 divided by 2. So w to the power 1 over 2 is going to be equal to 2 to the power 1 over 2, and here the value for k is going to be 0 and 1, and this is multiplied with e to the power of I k pi plus pi by 12. So let's find out the first one, which is when k is equal to 0. 2 to the power 1 over 2 into e to the power of I. 0 into pi is going to be simply a 0, so this is going to be a pi by 12. So the complex number w, the first root is going to be e to the power of I pi by 12. What about the second root? The second root is 2 to the power 1 over 2 into e to the power of I k pi, which is 1 pi in plus pi by 12. So the second root is 2 to the power 1 over 2 into e to the power of I 13 pi by 12. However, he has clearly mentioned that theta has to be between 0 to pi, and therefore we cannot use this. What we're going to do instead is to take the next root as going to omit this and then say w is going to be equal to 2 to the power of I 1 by 2 into e to the power of I minus pi plus pi by 12. Minus pi by plus pi by 12. So this is 2 to the power 1 over 2 into e to the power of I minus 11 pi by 12. Minus 11 pi by 12. So that is your answer for part C. Let's get part D. Alright, the complex number w can be expressed in the form a plus ib whole square. So w is root 3 plus I, and then he says w can be expressed as a plus ib the whole square. Right, that's what it means. That simply means that a plus ib the whole square is equal to a plus ib the whole square is equal to. Now I'm going to expand this using a plus b the whole square formula. A square plus b square, this is going to be I square, which is going to be a minus, plus I 2ab is going to be equal to root 3 plus I. So I have two complex numbers on the LHS and the RHS, and therefore I can go ahead and equate the real parts, and then I can also equate the imaginary part. Now I can write b as equal to 1 over 2a. I'll take the value for b and substitute back in the equation. So that's 1 over 2a the whole square, and that's equal to root 3. So what are we going to have here? We're going to have a square plus a square minus 1 over 4a square is equal to root 3. Taking an LCM, this is going to be 4a to the power of 4 minus 1, and that's equal to 4a square root 3. Transposing it back. So this is the equation I'm left with. I can't do splitting of the middle term over here because the equation is not factorizable. So what am I going to do next? Well, I'm going to be using the formula to solve for this one. Alright, so let's see what's the formula. I have x is equal to minus b plus or minus root of b square minus 4ac. So I'm going to use that and say a square is equal to minus b, which is 4 root 3, plus or minus root of b square, which is going to be 4 root 3 the whole square, b square minus 4ac, 4 into a into a c, and that's divided by 2 into 4. So a square can now be written as 4 root 3 plus or minus root of 16 3s are 48. However, the square of a number has to be positive. Root 3 is going to be 1.71, and that divided by 2 is going to be a less than a 1 number. And if I subtract it with a 1, I'm going to get a negative number, and hence I'm going to discard the negative and just hold a positive value. And that is the value for a square. Let's go back and see if that's what he is asking for. And yes, I did. So using that, I'm going to now find the value for b square. Let's quickly do that. I know that b square, or b is simply that, so I'm going to use this and say b is equal to 1 over 2a. So b square is going to be 1 over 4a square. So here I can substitute the value for a square, which is root 3 by 2 plus 1. Root 3 by 2 plus 1. Now let's simplify this further. So b square can be written as 1 over 2 root 3 plus 4. Again, I'm going to be rationalizing the denominator. By 2 plus 1, or I can write this as 1 minus root 3 by 2. Let's now look at hence find the expression of tan pi by 12 in the form p plus q root 3. So how can I find out tan pi by 12? So let's see what is tan pi by 12. What I do know is that a plus ib, the whole square, is root 3 plus I, which means a plus ib is going to be root 3 plus I whole to the power of 1 over 2, which basically means that a plus ib is a square root of root 3 plus I. And I've already found the square root of root 3 plus I, right? So somewhere there. So I can see that the root has the argument, and then it has the modulus, and then the argument of pi by 12. Now this is what I'm going to be using here. Tan inverse of b by a, and that's going to give me a pi by 12. And that would also tell me that tan pi by 12 is equal to b by a. Tan pi by 12 is equal to b by a. Now what is b by a? I don't have the direct value for b by a, but I do have b square and a square. So I'm going to write this as root of b square by a square, and then substitute the value for b square and a square. B square is 1 minus root 3 by 2. Minus root 3, and therefore the value for p over here is a 2, and the value for q is a minus 1. Value for q is a minus 1, and that is the end of the solution. So I would like to discuss something interesting about the roots of a complex number itself. This is not really required for this paper. Again, I'm going to show you something on Desmos. So you can see here that I have plotted a complex number w, and the complex number w is nothing but root 3 plus 1. That's a complex number, and don't worry about these formulas. You don't really need to know this. I'm going to remove this point here. So you can see that there are 2 roots for this particular complex number. Okay, and those are the 2 different roots. This is root 1, and this is the second root that we found out. What I wanted to actually show you is, if I'm trying to find out more roots of a complex number, you can see that this is forming a equilateral triangle. And if I look for 4 roots, I'll end up with a square and a pentagon, a regular pentagon, and it continues to give me regular polygons. The next root is got by multiplying, this complex number by pi by 6 by 5, because I'm looking for 5 roots, so it's going to be a pi by 30. So the moment I multiply, I get that, and then again I multiply, and then I get this, and then I multiply. So you can also see that this forms a circle. Right? All the roots are going to be on the circle itself. So pretty interesting when you look at this on Desmos. You can see that as in when I increase and decrease, it's gonna keep on the all the roots on the circle itself, and it's always going to be equidistant, right? That's what I wanted to show you. Okay, so that's it for this video. Thank you.